All right, let's go ahead and do some of my favorite problems in all of this year. And so I really do enjoy Hess's law problems. They're like a puzzle. And so all you need to do is you need to flip these around, add them together, multiply them, do whatever you need to make them add together to equal this particular chemical reaction. Now, something to keep in mind, all right? So you want to make sure you are dealing with the correct substance and the correct substance in the correct state of matter. And so the state of matter matters in this situation. And so let's go ahead and talk about how we can do this. And so what I do is I just pick one of the things that I want it to become, and so I'll just go ahead and pick this one. And so where in these two chemical reactions is this particular PbCl2 solid? Well, it's right here. And so what you want to ask yourself is, in the chemical reaction that we're dealing with, is it on the correct side, and do we have the correct number of them? That's what you want to ask yourself. And so we do have the correct number of them, so there's one of them there, there's one of them there, but it is not on the correct side. And so what we need to do is we need to flip this chemical reaction. So we're going to flip it, and so I'm going to rewrite it down here, but flipped. Now, when you flip this, what ends up happening is if you flip a chemical reaction, you need to flip the sign as well. So the delta H was a negative 359.4, so now it's a positive 359.4. Now, what I personally like to do is when I do this, I like to underline that I've fixed this particular one. Now, what I'll say is, you could totally go here and you can fix this one as well, but because this is kind of a common, substance, like oxygen gas is common, hydrogen gas, or if it was water, I tend to save those common ones for last. And so, this one I'll do next. And so this first equation happens to have PbCl4 liquid. And notice how it is. So again, there's two things we need to ask ourselves. Is it on the correct side, and do we have the correct number of them? Well, that's yes to both. It's on the correct side and the correct number. So I'm just going to go ahead and write it underneath here. And this is what we end up with. And so what I want to then point out is, so we did fix this one. Now, if you take a look here, first off, notice how I put the arrows right on top of each other. And the reason why that is because it helps us see the left and the right more clearly. And the thing that we want to also remember is that if there is a substance on the left of one equation and on the right of another, you can actually cross those out. So notice how this here is on the right, and notice how this here is on the left. So because we have them on both sides there, we can actually cancel them out. Now notice how we have one of these here, and we have two of these here. Because there's only one on the right, that means it's going to cancel out one on the left. So because there's only one right here, and we have two over here, instead of it canceling out both of them, it's only going to cancel out the one, and we end up with just one Cl2. And so after you cancel these out, you can just add this together, and you get PbCl2 solid plus Cl2 yields PbCl4 liquid. And notice how this equation here is this equation. So notice how we took these two right here, we flipped them, we multiplied them, we added them together, we canceled things out, and we got it to become this. Now, all we need to do is once we are able to get it to add together to become this, The only thing we need to do now is just add the delta H's together. Now notice how the second delta H, we did end up changing that one because we flipped we flipped this particular chemical equation here. And so when we add these together, it's going to give us the delta H of the reaction. And so we end up with a delta H of positive 30.2. So again, this is Hess's law, and Hess's law states that if you can get different chemical reactions to add together to make a different reaction, the delta H's added together will give you the delta H of that reaction. So let's go ahead and do another one here. So again, we're trying to make it become this, okay? We're trying to make it become this. And like I said, I like to save like the hydrogen gases and you know, things like elements for last. So I'm going to go ahead and pick this one. I'm going to find this down here, which happens to be right here. And again, we're trying to find the delta H of this reaction here. And so when we are thinking about this right here, we need to ask ourselves, is this on the correct side, and do we have the correct number of them? And the answer is we do have the correct number, but it's not on the correct side, so what we need to do is flip it. And so we get 6 waters plus 5 carbon dioxides, yielding 8 oxygens plus C5H12. Now because we flipped it, again, this becomes a positive because you changed the sign. So when you flip it, you change the sign. So we fixed this one. So now I'm just going to go ahead and pick this one. Notice how this particular equation is the one that has the carbons. And so what I'm going to do is we need to ask ourselves, is it on the correct side, and is there the correct number of them? And the answer is it is on the correct side. However, we do not have the correct number of them. There's 5 carbons here, but only 1 here. And so the way you fix that is by multiplying everything by 5. So if we're multiplying everything by 5, we're going to end up having 5 carbons plus 5 oxygen gas, yielding 5 carbon dioxides. And because we multiplied everything by 5, we need to multiply the delta H by 5. Now, this next one here, actually has got a couple things going on with it. So we're going to try to fix this one. This one is the one that has the hydrogen gas. Notice how we do not have the correct amount, so what we need to end up doing is multiplying it by 6, but it is on the correct side, but we end up with 6 hydrogen gas plus 3 oxygen gas, yielding 6 waters. And again, because we multiplied it by 6, we have to multiply the delta H by 6. So now what we can do is cancel things out. Notice how we have 5 carbon dioxides here. We have 5 carbon dioxides here. Those cancel out. Notice 6 waters, 6 waters. Again, if one's on the left and one's on the right, they cancel out. Now notice how these here are on the same side. We have 5 oxygens on the left plus 3 oxygens on the right. This actually adds together. If they're on the same side, they add together to make 8 oxygens. But notice how we have 8 oxygens here, and that cancels out. So if they're on the same side, they add together. If they're on opposite sides, they cancel out. And then we're left with this. After we cancel everything out, we're left with 5 carbons plus 6 hydrogen gas, yielding C5H12. Now again, if we are able to add these together to get this equation, the delta H's added together will give us the delta H of this equation. And when we add these together, we get negative 146.7, and that's kilojoules per mole. All right. This happens to be an exothermic reaction because the delta H is negative. So that means it's going to give off energy when this reaction occurs. All right. Let's go ahead and do the last one here. Again, I just personally like to start with the least common looking one, and so this happens to be here. Okay, so that happens to be there. And so what we're going to do is we need to flip it and multiply it by 2 because it's not on the correct side and it's not the correct number. So we end up with 2 nitric acids, because again we're multiplying it by 2, making 2 waters plus 2 dinitrogen pentoxide. Now because we flipped it, this becomes a positive and we multiplied it by 2. Okay, next one. So what I'm going to say here is, let's just say that I randomly picked this one. Now, the reason why this is a bad one to pick is because notice how the two chemical reactions that are left over, the two chemical equations, both have oxygen in them, and so how do we know what to do with both of those? And so in this situation, I'm actually not going to do this one because those two have that, but rather I'm going to choose this one because there's only one chemical equation that has that, and it's this. And so it is on the correct side, but it does not have the correct number of them. And so what we end up needing to do is multiplying it by 4. So when we multiply that by 4, it ends up giving us 2 and 2, plus 3 times 4 is 12, divided by 2 is 602. All right, plus 2 hydrogen gas molecules yields 4 HNO3. All right, so there is a little correction that I need to make here. It's actually something that's wrong with the problem. If you take a look at this particular equation here, this equation is not balanced. To balance this, there actually needs to be a 2 right here. And so when there's a 2 right there, that's actually going to make, because we multiplied this by 2, it's actually going to make this become a 4. So the problem itself had an error, and the error was that this wasn't balanced. And so again, we flipped it and we multiplied the whole thing by 2, so that means this is a 4. All right, so now what we can do is we can move on to the next one here. Now first off, what I want to point out is this here cancels out. So let's go ahead and cancel out what we already have canceled out. So this cancels here. Again, those are the same thing on both sides, cancels out. Now the next thing I want to point out is we've fixed this one here by multiplying it by 4. So we end up multiplying this by 4. And now what we need to do is figure out how do we get 6 oxygens here. Well, there's a couple things going on here. I mean 5 oxygens. First off, we have 6 oxygens here already, so we already have more than we need. We also have these 2 here which we don't need. And so what I want to do is I want to point out that this particular equation, which I'm going to use a different color to write, this particular equation, we are using this one only to cancel things out. So the elements or the substances within this chemical equation are only used to cancel things out. So let's go ahead and see how can we use this to cancel out, let's say, the water. All right, so if we were to do this to cancel out the water, what we would need to do is we would need to flip it and multiply it by 2. And so we would end up with 2 waters, so we'd flip it and multiply by 2. And this would yield 2 hydrogen gas molecules plus 1 oxygen gas molecule. And so we flipped it, so that becomes a positive, and we multiplied it by 2. And when we did that, notice how this works out very nicely. This cancels out with the water. The hydrogen gas molecules cancel out as well. And then notice how we have 6 oxygens here, we have 1 oxygen here. This 6 oxygens will cancel, one of those will cancel out with the other one, and this will become 5, and then this one just cancels out. And so now we're left with this yielding that, which is exactly what we wanted. So what's left over is 2 nitrogen gas plus 5 oxygen gas, yielding 2 N2O5. Now all we need to do is add all of this together, and then once we do that, we get our change in enthalpy of the reaction. And when you add all of this together, what you end up with is the delta H of the chemical reaction is 41.4. And that's all there is to it. Like I said, these particular problems, I really enjoy them. They're kind of like a puzzle to me. Again, what you're doing is you're just flipping these around, you're multiplying them, whatever you need to do to get them to cancel out, to add together, to get your final equation, and then all you have to do is add up what's left over, and that's all there is. So come to class with questions. Have a great day, and take care.